Oh, why hello there, Algebra 1. Let's go ahead and look at our next target, which is LSPF1. Yeah, I know. Linear systems and piecewise functions, first target, LSPF1. I know. All right, so here we go. What we're looking at here is solving linear systems by graphing. That's a lot of things. We know graphing. We know what graphing is. What are linear systems? That's kind of the next thing. Linear systems, oh hey, a system of linear equations, also called linear system, consists of two or more linear equations that have the same variables. In other words, two or more that have like X and Y generally, okay? A solution, here's our important thing. A solution of a system of linear equations with two variables is any ordered pair that satisfies both equations. In other words, do they cross and where do they cross? Or where do they touch? What do I mean by that? If I look at graph A, I've got two lines here. Look at those two lines. Are they the same line? No. Do they touch? Yeah. Right there. And that would be my solution. If I had values in here, I could tell you what that point was, what that coordinate point was, okay? If I've got two lines that intersect at one point, that's my one solution. Graph B, this looks like one line, but it's not. They're coincident lines. In other words, they're the same line. How many times does the same line touch itself, touch one another? Either way, it's weird to say it. But if I've got the same line, every point touches every point. Every point on one line touches the same point on the other line. In other words, since they're the same line, I would have an infinite, and then we use this one, the sideways 8 kind of thing, infinite solutions. Up there we had one solution. Can you think of any, oh wow, there we go. Can you think of any other way that two lines interact? Well, if you flipped ahead in the book, you can, or maybe you thought about it. What if you had, I don't know, parallel lines? Parallel lines, how many times do parallel lines touch? I don't say it's a trick question, but at the same time, we know that parallel lines never touch. That's what makes them parallel. If they don't touch, if they don't intersect, they have no solutions. So when we're talking about systems of linear equations, or linear systems in this case, we're going to solve this by three ways. One way we're going to solve it is graphing, LSPF1. One way we're going to solve it is elimination, LSPF2. Then we're going to solve it using substitution. Oh, I might have gotten those wrong or backwards. Anyway, substitution and elimination methods, LSPF2 and LSPF3, whatever those are, okay? Let's take a look at how to figure out where two lines cross, if two lines cross or touch, by graphing. Solving consistent, independent linear systems by graphing. A consistent system, bold words, is a system with at least one solution. Consistence can be either independent or dependent. Independent is our exactly one solution. I am independent and I am by myself, therefore I have one solution. It's dependent would have infinite solutions. This is when it's the same line. This one, the dependent, is the same line. Dependent, same line. If it doesn't have a solution, if they are parallel lines that do not touch, we call this an inconsistent system. Now, I am not going to be asking for those words. You need to understand that they exist, but I'm going to be asking how many solutions do they have. I'm not going to be asking the type. Okay. Let's take a look at this. It says, solve the linear system, or solve the system of linear equations by graphing. Check your answer. Well, we've been building towards this, right? We have talked about several different ways to graph. We have done graphing by intercepts. We've done graphing by picking a couple of points of X and Y and then plotting them and drawing our lines. We've done point slope and slope intercept form graphs. We've done all of that. What we have here now is this. We have 2x plus y equals 6 and negative x plus y equals 3. This thing, this little curly bracket on the left-hand side, that's what indicates our system. That's a system, 2 equations right there. Now, I agree. If you see these equations like this, you could absolutely do intercepts. Find the intercepts and graph them. That's what they did. Okay. They say find two points, or find 2 points and then graph it, check it or something. I don't. Find the intercepts, graph each line independently, see where they cross. That is absolutely one way. Remember, intercepts, an x-intercept is when y equals 0, solve for x. The y-intercept, when x is 0, solve for y. Okay, that's intercepts. Another way is, what if it was in slope-intercept form? What if it was y equals mx plus b? This set of linear system, or this linear system, could be efficiently done. We could solve both of these for y. Y equals negative 2x plus 6. Y equals x plus 3. If I was doing that top one, I would plot 0, 6 as my y-intercept. I go down to right 1, down to right 1. And I could draw my line through those points. Or if I was doing y equals x plus 3, my y-intercept is 3. My slope is 1, so I would rise 1, run 1, rise 1, run 1. I would draw my line through my points, and you will see that no matter which way we graphed it, what do we end up with? Our solution is 1, 4. And then probably the most important part here, check. It looks like they touch at 1, 4, but graphing is one of those things that's very interesting. Graphing is only as good as the lines that you draw, which means I'm in trouble unless I'm using a ruler. Graphing is only as good as the lines that you draw. So in other words, you're going to want to check your solutions. If we do that, what we're going to do, we said that they touched at 1, 4, they intersect at 1, 4. What I'm going to do then is I'm going to take both initial equations, plug 1 in for x, 4 in for y, and see if these equations are true. And it turns out that these are. Since those are both true, our solution is 1, 4. You're probably going, whoo, this is a little bit. That's okay. That's okay. Let's go ahead and do one on our own. Let's do one on our own here. Let's go to the next page. This one says, find the intercepts for each equation plus a third point, then check and graph. I don't want to do that. Here's what I'm going to do. I'm going to look at these independently. I have this top equation that's y equals 2x minus 2. That is in slope-intercept form. I'm done with that one. I'm just going to graph that one. I can do that because I know how to graph using slope-intercept form. My y-intercept is negative 2. My slope is 2. My m is 2. So this is like rising 2 and running 1. Up 2, right 1, up 2, right 1, up 2, right 1. I didn't have to do all those points, but I did. Then very carefully draw my line. Now, since I see this second one, this second equation here, we'll put this in this reddish color here, 3y plus 6x equals 18. Could you put this in slope-intercept form? Yeah, and it would actually turn out okay. If you see it like that, more power to you. I think this one, this is called standard form, kind of, it's a little bit modified, but I think this one works well for finding intercepts. And here's the reason why. I've got both variables on one side and then my constant on the other. So if I was trying to find, I'm going to use this right here. I'm going to ignore this third point, ignore this over here. I'm going to find my x-intercept. My x-intercept, again, this is when y is 0. So I would have 6x equals 18. So x would equal 3. Plot 3, 0, because that's my x-intercept. It intercepts the x-axis at 3. My y-intercept is when x is 0. So 3y equals 18, or y equals 6. Y equals 6 right there. And here's what I'm going to do. I'm going to draw a line between these 2 points the best that I can. And holy cow, look at that. Even Mr. Brayman drew it okay enough. It looks like they intersect right there. That point right there, they appear to intersect at 2, 2. I'm proud of myself right now. That looks pretty darn good. Now we need to check. This is what's beautiful about this target. Checking your answers is efficient. Check your answers. Plug 2, 2 into both of these. So this first one, does, I'm gonna have a little question mark in here. Does 2 equal 2 times 2 minus 2? Does 2 equal 4 minus 2? 2 does equal 2. This first one is correct. It holds true. The second one, if I plug 2 in for x and 2 in for y, 3 times 2 plus 6 times 2, does that equal 18? Well, 3 times 2 is 6, 6 times 2 is 12, and 6 and 12 do add together, do sum together to get 18. This one's also true. So guess what? Our solution is 2, 2. Whew. Put some parentheses around that guy, right? Because it's a coordinate point. Ah, I love it. I love it. If you can't tell, we're on some of my absolute most favorite targets. Hands down, some of my most favorite targets. Well, you know what time it is. It's your turn time. Graph, see if they intersect, check your work, go. All right, now that we're back, go ahead, check your answers here. This does look pretty darn good. The first one, I like both of these. I think both of these you can do any way you want to, but number 3, I just graphed it using slope intercept form, and I did intercepts for the other one. You could do whatever you want though. I found that it intersected at -2, 2. I checked my answers and I was right. Number 4, I said I'm going to graph the first one using slope intercept form, and the second one I'm going to use intercepts. And I think they crossed at -2, 4. And I checked my work, and it turns out, guess what? They did again. That's what we're trying to do. Graph them, see where they cross, then check your answer. There we go. That is our job. That is our job. Okay. What if we have a special linear system? Special linear system. Okay. I'm going to look at this one right here. I'm just going to graph this one without even kind of just ignore everything here. It says y equals 2x minus 2. So if I do this, y equals 2x minus 2. So my y-intercept is -2. I hate when they switch these around. -2x minus 2. My y-intercept is -2. My slope is +2. Up 2, right 1. Up 2, right 1. I hate when they switch these things around. Okay. Our second one, I'm actually going to solve that for y. That's a one-step equation to solve for y. Y equals 2x plus 4. Oh, that's interesting. That's interesting. My y-intercept is 4. My slope is 2 again. These things right there are parallel lines. And you know how I know they're parallel lines? We found right here, the slopes are the same. If they're the same slope, but a different y-intercept, they're never going to touch. So this one you would say has no solution. No solution. Let's check another one. Let's just check part B here. Oh, I like this one. This one's already in slope intercept form. This one's a one-step equation to get to slope intercept form. I'm going to do that. The top one's y equals 3x minus 3. So if I add 3x to both sides, y equals 3x minus 3. Before we even graph, we're going to do it anyway, but before we graph, these are what? Yeah, these are the same line. These are the same line. I mean, I'll just draw it for us. Why not? Dude, these are the same line. Okay. Since they are the same line, we would say that this has infinite solutions. I love it. I love it. I know I went a little quick there, but we're getting the hang of this. We've been graphing. All right, we've been graphing. So your job right now, numbers 5 and 6. These are going to be special systems. I'm looking at that. I almost think that those are also pretty efficient to solve for y. That's what I would do anyway. Do that, graph them, see if they touch. All right, as you come back, you'll notice and checking your answers here. If you solve number 5, you saw that second one for y, you get y equals negative x minus 2, and you graph them, they're the same line. It's an infinite number of solutions. Just like number 6, you end up seeing right here, you can check this real fast. You've got the same slope, but different y-intercepts. Same slope, different y-intercepts. Parallel lines, they're never going to touch. They're never going to touch. So again, this is solving by graphing. What's the point of doing all this? Well, what we're going to do now, we're not do the estimating part. We're going to go right to the interpreting. Okay. What we're going to do is we're going to create equations just like we've been doing, create equations and then seeing where they cross to interpret them. What we have is Rock and Bowl charges $2.75 per game plus $3 for shoe rental. Super Bowling charges $2.25 per game and $3.50 for shoe rental. For how many games will the cost to bowl be approximately the same at both places? And what is that cost? In other words, what we're going to do is create 2 equations and then graph them and see where they cross, basically. Okay. So for Rock and Bowl, we get $2.75 per game. Oh, there's that per word again. And then $3 for shoe rental. This is like y equals, if so, per game, $2.75 per game. There's our slope, right? We see that slope business there. The other one is $2.25, and then $3.50 for shoe rental. We're going to create two equations here. Our first one is y equals $2.75 per game, so 2.75x plus 3. Our second one is y equals 2.25x plus 3.5. And if we do that, what happens is x is games, y is cost. Okay, we've got our system of, this is our system of linear equations. Let's graph them and see where they cross, I guess, right? The first one, my y-intercept is 3. My slope is 2.75, 2 and 2 3/4. I'm going to do the best I can. Up 2 3/4 and right 1. Up 2 3/4 and right 1. Okay, this is, oops, I forgot my right 1. 2 3/4, right 1. These are my games on the bottom. It even tells you what x and y are here too. Up 2 3/4 and right 1. This line right here, this is Rock and Bowl, R and B. Let's do Super Bowling a different color here. Super Bowling, my slope or my y-intercept is 3.5. 3.5, and my slope is 2 1/4. So up, let's see here, 1 2 1/4, right. Oh, I think I see it already. I'm gonna draw that. It looks like that they cross right there. Looks like they cross at, that can't be right, can it? No, that's not right. 1 game? Wow, that'd be weird. It looks like it's like 1 and almost 6. I know it's not quite 6. It looks like 5 3/4 maybe. 5.75. I mean, we could try 6, right? Let's try the 1 and 5.75. If we do that, well, does 2.75 times 1 plus 3. Well, that is 5.75. That's kind of interesting. That's for the Rock and Bowl. And then 2.25 times 1 plus 3.5 is also 5.7. Oh, okay. If you would have checked 6, you would have seen that it came close, right? That's our estimation. And yeah, this makes a lot of sense. So it's kind of weird. It appears to intersect there. So After one game, the cost will be 5 3/4. Now you might have seen that mathematically, and that's okay. We're going to get into that. All right. What I want you guys to do here is to go ahead and check number 10. So you guys try out number 10 and see what you come up with. Find that estimate. All right. So welcome back. I got Video Club A and Video Club B. A, I said was y equals 4x plus 10, with x being the number of movies and y being the money. B was 3x plus, or y equals 3x plus 15. And then I graphed both of those, and it looked like, and I think they did, they crossed right there at 5 movies and $30. We solved it by graphing. Again, it's only as good as your line that you draw. If you're a little bit off, you could check your work and we're going to be okay with it. This is a great way to estimate. Graphing is not the best way to find the exact solution, but it will give you a rough solution quickly. So with that said, that takes care of LSPF1. Take care. Have a fantastic day.